Alright guys, so today we're going to be starting our astrophysics unit. Congratulations, we're on the final unit of IB Physics. This has been a long time coming. Um, so I'm pretty excited to talk about astrophysics with you. So astrophysics is an option topic, and what that means is that, so basically you have the 8 core topics that we've covered. You've got uncertainty and measurement, mechanics, thermal physics, waves, electricity and magnetism, circular motion and gravity, atomic and nuclear physics, and particle physics, and then you have energy production, which we just finished topic 8. So astrophysics is not one of the 8 core topics. It's an option topic, and there's 4 different option topics. I always choose astrophysics just because, in my opinion, and based off of what I've heard from other IB physics teachers, astrophysics is the easiest one. It just so happens I also think it's the most interesting one, personally. If you do want to know anything about the other option topics, please consult your IB physics textbook. Now, something else to know about astrophysics is this is a specialized unit to the IB. This is not stuff that I learned in college, and so a lot of this stuff I'm not, 100% expert on. I would definitely consult your IB physics resources for clarification on stuff. But this is one of those units, just like topic 8, that because it's unique to the IB physics curriculum, your textbook is really, really the best resource for you. So the way that the option topics are assessed on the IB exam is you have paper 1 and paper 2, which cover the 8 core topics, and then you have paper 3, which is 20% of your IB grade. Paper 3 includes some free response questions and also some data analysis questions, which we can talk about later. But the 2 to 4 free response questions are over one of the 4 option topics. Of course, since we're doing astrophysics, that's option D, you would only answer the questions over option D. Now, I can't stop you from answering questions in other sections, but please, please, please only answer the questions over option D. So this option topic has 3 chapters. D1 is stellar quantities, D2 is stellar characteristics and stellar evolution, and D3 is cosmology. Okay, so we're going to start with D1. Basically, D1 is called stellar quantities, and it has 3 primary parts: looking at objects in the universe, astronomical units, and then luminosity and apparent brightness. Okay, so please, as we go along, don't forget that definitions are important. So here are the understandings and applications and skills for astrophysics. You have to be able to understand objects in the universe. We'll talk a little bit about that today. The nature of stars. We'll also talk about that in this video. And then astronomical distances, stellar parallax and its limitations, and luminosity and brightness. Apparent brightness. Applications and skills. You must be able to identify objects in the universe qualitatively. That means with words and not numbers. Qualitatively describing the equilibrium between pressure and gravitation in stars. That's pretty easy. We'll talk about that later. Using the astronomical unit, the light year, and the parsec. Describing the method to determine distance to stars through stellar parallax. And solving problems involving luminosity, apparent brightness, and distance. Okay, so that's everything in D1. And then just for some guidance, here is some things to know about D1. For this course, objects in the universe include planets, comets, stars, planetary systems, constellations, stellar clusters, nebulae, galaxies, clusters of galaxies, and superclusters of galaxies. Now, this is why the first assignment I gave you was to just take down notes and from your textbook and from the PowerPoint slide, because a lot of these things are not things that really need to be explained in any depth, but they're kind of definition-y type of things that you just need to be aware of. Students are expected to have an awareness of the vast changes in distance scale from planetary systems through to superclusters of galaxies and the universe as a whole. This is where you're going to want to look at those Khan Academy videos. Okay, so Khan Academy, I posted some videos for you to use on Khan Academy. Please check those out. Those pertain to the scale of the universe. Now, what equations are given to you in the data booklet? The first one we'll see later. This has to do with something called parallax. And again, we'll get into that later. Is that how you spell parallax? Hopefully. The second one should look kind of familiar to you actually. This is actually basically the Stefan-Boltzmann law with an emissivity of 1 for a perfect black body. And in this case, instead of calling it power, we call it luminosity, the luminosity of a star, but it's basically the exact same thing. Okay, so that's something we're very familiar with. B, if you look at this equation right here, B equals L over 4 pi d squared, that should also look somewhat familiar to you. In fact, it should kind of remind you of the solar constant calculation, where you take the power that the star puts out, which again in this unit we call luminosity, and divide by 4 pi d squared, where d is the distance from the star to the planet you're talking about. Okay, so some of these concepts we've actually kind of seen before. Okay, so moving on. And again, a lot of these things are just kind of definition-y things that you just need to take down in your notes. They don't require a lot of explanations. You should know some things about our solar system. We have 8 planets in our solar system. They orbit the sun in an elliptical orbit. If you don't know what an ellipse is, Google it. It's basically like an oval. We talked about that before. In addition to the 8 planets, we also have the asteroid belt, which has a bunch of asteroids kind of in the region between the orbit of Mars and the orbit of Jupiter, and some various comets and asteroids in orbit around the sun. And again, this is just kind of outlining the general structure of our solar system. These are things you should know as it is, that you should just put in your notes. And again, just kind of clicking through here, just some basic things. Now, do keep in mind you don't need to know any of these values or anything, but you should kind of understand the order of the planets just in case any questions like that come up. By the way, somebody asked why Venus has such a high temperature compared to Mercury. If you look at the albedo of Venus, the albedo of Venus is actually higher than the albedo of Mercury, which means the planet Venus is more reflective. And so you might kind of expect that Venus would be a colder temperature. It's actually a higher temperature, and that's because its atmosphere has a very, very strong greenhouse effect, and Mercury does not really have too much of an atmosphere. So that's why Mercury is colder than Venus, even though it's closer to the Sun, and it has a lower albedo. So, fun fact. Again, these are just some things you need to put into your notes as far as, what is an asteroid, what are comets. I think it's all kind of self-explanatory. Here's a picture of an asteroid. The difference between asteroids and comets are asteroids are kind of more rocky, whereas comets tend to have more ice and gas trapped in the ice. And the gas, as the temperature increases, tends to give off light, which is why comets tend to have like tails like this that you can see, like shooting stars. A shooting star is a comet, basically. And you can read what it says on this slide about where comets come from and whatnot. Okay, so let's talk a little bit about the sun. Again, you don't really need to know any of these values exactly. You should have an idea of the order of magnitude of the mass and radius of the sun, but you don't need to know any of these values. The surface temperature of our sun is about 5,800 Kelvin. That's a kind of medium temperature. It sounds really hot, and it probably is from our perspective, but there's a lot of stars in the universe that are much hotter or much colder than that. So our sun is actually pretty average. So what we're going to talk about now is how do you form stars? And again, I will post videos about the formation of stars that you should watch through Khan Academy because they can do a much better job of explaining it than I can. But this is essentially how stars form. If you have just, let's say, a bunch of hydrogen out there somewhere in the universe, and the reason the hydrogen is formed is just because when the universe formed and you had, all the protons and neutrons and electrons just kind of out there separated, the easiest atom to form is obviously hydrogen because it only has one proton. Okay, so that's why most of the universe, actually about 75% of the universe, is made of hydrogen. So let's say, hypothetically speaking, you have a bunch of nebula gas out there. You have a bunch of hydrogen, maybe some other elements, but primarily hydrogen. Last year we talked about gravity and how gravity is an attractive force that kind of pulls everything together. And so what happens is if you have a giant cloud of hydrogen out in space, gravity is going to pull that gas together. Now, it might happen very slowly. It could happen potentially over thousands or millions of years. But eventually, gravity is going to pull the clump of gas together. And as the gas gets pulled together, because it gets closer together, gravity is stronger. And if gravity is stronger, it pulls it together faster. And so it's going to kind of like accelerate inwards. The cloud is. And as the cloud becomes more dense, the temperature increases, because that's how gases work, of course. Smaller volume, more temperature. As the temperature of the gas increases, eventually you get to the point where the temperature is so high, fusion can occur. And we've talked about the super high temperatures needed for fusion before. They're not quite as high temperatures in stars, just because there's also a lot of pressure in there because of the gravity. But you still need really high temperatures for fusion to form. By the way, there are some objects called brown dwarfs out in the universe, which is basically what you get when a star did not actually become a star. You had a bunch of mass, but it wasn't quite enough mass to reach the high temperatures needed to cause fusion. So if you're interested, you can look at brown dwarfs later. Those are kind of like would-be stars that didn't quite make it in life. Now, what happens when the star is formed is you always, well, I say always, you typically have an equilibrium reached between two opposing forces. Okay, fusion generates a lot of outward radiation pressure. It says outward radiation. Really, it should maybe say outward radiation pressure, and that just comes because of the high temperatures and heat coming out of fusion. Fusion produces a lot of energy, as we've talked about before. And you can imagine if you take like a balloon and you heat up the balloon would expand. And this is the same type of thing. All that fusion that stars creates an outward radiation pressure. Now, you also have an inward radiation pressure from the gravitational force, because all that gas has mass, and mass attracts towards itself, like we've talked about. Typically, in most stars, you have an equilibrium reached between the inward pull of gravity and the outward radiation pressure. And that is something you need to be able to explain, because you often see questions about that. And typically, stars can remain in this kind of stable equilibrium for millions or billions of years. Our sun is currently in that state. Now, later, at the end of the star's lifetime, we'll talk about what happens later on. But eventually, as the star loses mass, it can grow in size and change its temperature, just because as it loses mass, there's less gravitational force pulling the star inward, and so it can grow in size over time. And then this slide just kind of talks about that. I don't know if there's anything new on there. You can read that slide on your own, pause it if you want. I also don't think there's anything new on this slide. This is maybe like a nice way to visualize what's happening as far as that stable equilibrium between the outward radiation pressure caused by fusion and the inward gravitational pressure caused by gravity. And you can kind of read that on your own. Okay, so as far as the basics of how a star works, there you go. Okay, so definitely watch the Khan Academy videos that I'm going to be rolling out for more details about formation and lifetime, or the lifetime of a star. But we'll come back to that later. So just to get a few kind of definition-y vocabulary things out of the way, you have binary stars and stellar clusters. A binary star is basically where you have two stars that rotate about a common center of mass. We think, at least the last time I made this PowerPoint, we thought that about half of stars closest to the sun are binary systems. That would look something like this. Okay, where you can see two stars kind of orbiting a common center of mass. And they don't have to be the same size. They could be completely different in size. But this is just to show you what that would look like. Okay, that would be a binary star system. If you've ever seen like Star Wars and you've seen like, oh, there's like two suns in the sky, that's a binary star system. And then you also have a stellar cluster. A stellar cluster is a group of stars that are positioned closely enough to be held together by gravity. And again, that's kind of a definition-y type of thing that you need to be aware of. Stellar clusters, because they're all that close together, that means all of the stars in a stellar cluster were probably formed at around the same time. And these are just some images. You do need to be able to distinguish between a stellar cluster and a constellation. And you can write down the definitions in your notes, and you should. But basically, a stellar cluster, the difference between a stellar cluster and a constellation is a stellar cluster is a group of stars physically near each other in space. Now, you might not be able to see them physically close to each other, but they are. A constellation is just a group of stars that forms a pattern. But it's very possible for stars to form a pattern to us as seen from Earth, but they're not necessarily close to each other in space. Okay, so that's the difference between a stellar cluster and a constellation. And then these, I'm just going to kind of skip through. You can read what those say on your own in the notes. And you can read about this as well. Again, a lot of this stuff is just kind of definition-y stuff that you can just put in your notes. I do want to talk about what a nebula is really quickly. A nebula is a region of intergalactic dust and gas. And this is basically where stars are born, because we talked about before how stars are formed when you have like a bunch of like gas and dust just kind of out there that attracts inward because of gravity. So that's where a star is born. Now, where do nebulae come from? We'll talk about that later. Okay, but these are also called stellar nurseries because that's where stars start their lifetime. Okay, so here are just some pictures of a couple different nebula. Very pretty pictures. Okay, galaxy. Again, this is just kind of a definition thing. Here's some different galaxies. Galaxies are really just kind of big groups of stars. Again, I would definitely check out the Khan Academy videos I have posted just to understand the scale of the universe. And I think for the most part, we've talked about these things before. These are just some more pictures. Planetary nebula, we'll talk about that later, but it says they form from the gaseous shells that are ejected from low-mass giant stars when they transform into white dwarfs. And so I don't want to get into the lifetime of a star too much, but basically a lot of stars, what happens is over time, over millions or billions of years, as they lose mass, they expand. When they lose too much mass, you don't have that equilibrium anymore, because as they lose mass due to fusion, there's not as much force going in from gravity, and so over time the radiation pressure wins. And what happens when a star gets to that point in its lifetime is it's going to expand into what's called a red giant. And again, we'll talk about that later. But at some point, there's just not enough gravity to hold the star together, and so the outer shell of the star is just going to kind of puff away. You can see that in this video. The outer edge that you can see right here, that is what the planetary nebula is. That could possibly form another star someday. And then at the center of what used to be the red giant, you have what's called a white dwarf. And again, we'll talk more about that later. And then you have supernovas, which you can get when really big stars die in like crazy explosion-y ways. And that's something we'll talk more about that later. So we are just now on slide 51. I'm going to go ahead and stop there. I just really want to go through the basics really quickly. The next video will be over astronomical distances. We'll get into the next part of D1. I would highly encourage you to make sure you are taking really good notes. Make sure you are doing all of the work that I give to you, reading your textbook, doing the Khan Academy videos. I'm really trying to be selective about the ones I give you so that you get some supplemental material to better understand these concepts, since I'm not there to explain them to you in person. So hopefully you found this helpful. Please let me know if you have any other questions.